Okay, again, there's a lot of slides here. I'm not going to dwell on. I'm just going to do the important stuff. Okay? You all you've all heard of gravity. Mr. Newton came up with the theory of gravity. Okay. All right. So here's the deal. The quantum theory of gravity is the correct theory. We don't have it yet. Okay. So for instance, if you wanted to describe the very first moments of how the universe came about, you would need a quantum theory of gravity. If you wanted to describe what's happening inside a black hole, you need a quantum theory of gravity. Okay? So this is not, we don't have a quantum theory of gravity yet. It's waiting for one of you guys to come up with it. Okay? So in very extreme situations is when you would need this. So for instance, if you wanted to describe the first 10 to the minus 34 seconds of the universe's existence, you need this. Okay? All these theories are approximate theories. Okay? So for instance, general theory of relativity, if you are close to a black hole and stuff like that, outside a black hole, you would need this theory. So this is an approximation of that theory. If you want to describe the gravity of the Earth, all you need is Newton's laws. Okay, so this is even a more approximate theory. Okay, now this theory, so to give you guys a flavor, this was in, let's say, 1700. This didn't come about till 1925. So to go from here to there, it took 225 years. And this one, we've been roughly trying it for, let's say, close to 100 years. A lot of bright minds have been trying it for 100 years. We're nowhere close. Okay? So these are all giant leaps. Okay? All I'm telling you is this would be the final theory. We don't have it. Here's an approximation, which we got 100 years ago. Here's the approximation we use, okay, in most of our situation. And we have this theory for 300 years now. All right, so this is what we mostly talk about. You guys get a sense for it? You guys understand? Okay. Okay, what Mr. Newton said was, you can take any two masses. It doesn't matter what it is. 2 chairs, two horses, 2 elephants, 2 planets, 2 stars, any 2 objects. Okay. They attract each other. And what Mr. Newton gave you was the formula for the strength of their attraction. Okay. So this guy attracts him, and this guy, according to Newton's third law, attracts him with an equal and opposite force. So let's say if this guy attracts him with a 10-pound force, what does this guy do to him? What does he do to him? If this guy attracts him with a 10-pound force, this guy is attracting him with a 10-pound force. Okay? So for instance, Earth attracts me with a force of 160 pounds. What do I do in turn? I attract Earth with a force of 160 pounds. Okay. What Newton gave us was the magnitude of this force is given by this formula. It's given by the product of their masses divided by the distance squared. Okay? And this proportionality constant is the same no matter what the mass is, what objects are attracting each other. So this is called the universal gravitational constant. Okay? Now we'll talk a bit about this guy. This guy, in all of physics, this guy is the least accurately measured constant. Okay? In fact, this was not measured till 100 years after Mr. Newton came up with this formula. That's how difficult it was to measure it. Okay? And the force of gravity is weak because this constant is very small. Okay? All right. Now let's understand a couple of things about this, this formula. Okay, so let's say this is the sun and this is Earth. Let's say we double the mass of the sun and double the mass of the Earth, keeping the distance the same. You double that, the force increases by a factor of 4. Okay? If you double the distance between two objects, double R, 2 squared would be 4, so the force decreases by a factor of 4. Okay? All right, so that's Newton's universal law of gravity. Okay. Now, like I said, this number is very small, and hence the gravitational force is the weakest. So if you want to have a noticeable force, okay, this number is there. There's the gravitational constant in SI units. So if you want to have a noticeable force, at least one of the masses better be large. Okay? So you can calculate the force between two people, and these masses are 100 kg, 100 kg roughly, and this force would be, and let's say two people about 1 meter apart, that's 1 meter, 100, that's 10 to the 4, times 10 to the minus 11 is 10 to the minus 7. That's a tiny force. Yeah. So, yeah. So, I don't fall towards the chip because the force with which it's attracting me is very weak. Whereas, if I jump on, now I fell toward the earth, that force is much larger. Okay? And then I'll fall toward the earth. All right, so again, for the force to be noticeable, one of the masses has to be large. Okay, so here's an example. The force between these two guys is about 10 to the minus 7 newtons. That's the weight of 10 micrograms, and 1 microgram is the weight of all the carbon in that period. Okay, so the force between these two guys is the weight of 10 of these dots. Okay, that's how tiny it is. Okay. Whereas the force between this guy and this object is about 1,000 newtons. Yeah. So what have we learned so far? What all objects attract each other? Everything attracts everything. Okay. All right. Now, it turns out that, so here's a pretty neat fact actually. Is anything stationary in the universe? Nothing is stationary in the universe. Okay. Even Einstein made this mistake when he came up with this theory of general relativity. He thought that you go out in the night sky and you see everything sort of is static. And he thought the universe was not expanding and everything was static. The galaxies were all pinpointed. So now that we think about it, now that we thought about it more, everything in the universe is moving. Okay. Nothing is static. All right. And it turns out that galaxies are moving and they could be on collision courses and stuff like that. And in fact, we live in a spiral galaxy and we are on a collision course with the Andromeda galaxy, okay, and we'll collide in 4 billion years. So if you want to see really good fireworks, you can come back in 4 billion years. All right. So Newton came up with the theory of gravity in, what was it, 1687? Yep, 1687. Yeah. And so there was a formula for And I said this constant was not measured till 1800, 115 years later. Okay? And that was because it was very tiny and so very hard to measure. Okay? And here's the experiment that Mr. Cavendish used to measure it. Okay. So now you can do the following. I'm going to just take 30 seconds to describe it just because it's a pretty experiment. Okay, let's imagine you all right, so here's a rod with two heavy masses hanging, and you suspend it by a metal wire. Okay? Now in lab, it's easy to do. Now the stiffer the wire, harder it is to twist the wire, right? Now that can be measured. Okay? So you can measure what force it takes to twist this wire. Everybody understand that? Okay. So that's what this is. So here's a wire with two masses hanging there. Okay? And there's the wire whose properties you measured. How much torque does it take to twist the wire? Okay? So here you got this suspended. Now what you're going to do is you're going to bring these two heavy objects that were on the floor, you're going to raise them up. Okay? So as soon as you raise them, one on this side, one on this side, what happens? This guy is going to attract him, this guy is going to attract him. But remember, these are fairly small masses, let's say 5 pounds or whatever. And so the force will be tiny. How much will it twist? Very small amount. Did you guys understand that? Okay. So this wire will twist ever so slightly. And you are to measure this in 1800. How do you measure this tiny twist? It's probably a hundredth of a degree or something like that. So here was his brilliant idea. What he did was he put a mirror on that wire and he shines a laser beam on that. And that laser beam is reflected. Okay, when the wire twists, that beam of light moves over there. So that is sort of a magnifier. Do you guys understand? Okay. So when the wire twists a little, that beam of light, that laser beam, moves from that spot in the wall to that spot. Okay. And then he was able to measure the force between these two guys and able to calculate that, G. Okay, so in 1798, Mr. Cavendish measures G, and instantly, that very instant, we knew the mass of the Earth. How do we know the mass of the Earth? So here's the Earth, and here's you. The force between you and the Earth is mg. The force between you and Earth is mg equal to gmm divided by r squared. R is the radius of the Earth. You know the radius of the Earth. We've actually known the radius of the Earth almost 2,000 years. Okay. Your mass cancels. Have you ever measured G? You measured it 10 times in lab. Okay. And so we knew G, we knew this. Soon as this guy was measured, now you know the mass of the Earth. So for the first time, we found the mass of the Earth when we measured G. Okay? And so this happened in 1798. We had no idea before that. Okay? So that's why we call this the weighing the Earth experiment. But actually it was measuring G. Okay? And like I said again, it's still the least accurately measured quantity. Okay. Now, soon as we measure the mass of the Earth, you can calculate the density of the Earth. The density is, of course, mass divided by volume. Okay, we knew the radius. Now that we know the mass, you can calculate the density, and the average density of the Earth is 5.5 grams per centimeter cube. Okay, a centimeter cube is cc is roughly this much as a centimeter cube. Okay, so the average mass of the Earth is 5.5 grams per centimeter cube. But you go outside, the dirt outside is only about 2.3 grams per centimeter cube. So instantly we knew that the Earth had to be denser inside. The density was not uniform. Okay? One measurement opens up so many doors. Okay? So today here's the density profile. And you see the density at the surface is about 2.5 grams. Okay? 2.3 grams per centimeter cube. So here's another interesting story. Okay. What is the radius of the Earth? What is the radius of the Earth? 4,000 miles. Okay. 6,400 kilometers. Anybody know the deepest hole we've dug?
Was it done by the Russians?
I'm sorry?
Was it done by the Russians?
Yeah, it doesn't matter. All humanity is one. What is the deepest hole we've dug? It's probably one of the mines, diamond mines. Huh?
100 meters?
No. 4 miles, roughly. Okay, from here to the beach. 4 miles is barely scratching the surface. That's 0.1%. So who made up this picture? Do you guys understand? Okay. So how do we know this? This is a picture that's only about 40 years old, 50 years old. Okay. So here's how we know this. Okay. Here's an earthquake that's happened, that's occurred, and here are earthquake waves traveling. And we've detected these in seismometers. Now, okay, so here's a light beam. How does it travel? In a straight line. I mean, this is a wave. Why is it bending? So, a wave will bend anytime its velocity changes. Okay, any wave, a light wave, seismic wave, sound wave, anything will bend when its velocity changes, and its velocity depends on the properties of the material. Okay, so from the paths we can calculate the velocities and we can reconstruct the property of the medium. Okay, so that's how come we know this detailed picture of the interior of the Earth. And so for this kind of stuff, it takes data from hundreds of thousands of millions of earthquakes and millions of seismometers. Okay, so that's a supercomputer problem. Okay, and that's how we know it. Okay. Now here's an interesting thing about gravity. Okay. That Mr. Newton had figured out. Okay, so here's a satellite going around the Earth. Okay. Now, if you're going close to the surface of the Earth, like the space station, how far up is the space station? I'm sorry? Yeah, no. What is this distance? 250 miles. So, and that's 4,000 miles. So roughly 10% the, okay? 4,000, 400, 10%, okay? All right, so you're going at about 28,000 kilometers per hour. Now let's ask you this question. Let's say I go home and I turn the Earth into a black hole. Yeah. All I have to do is to turn the Earth into a black hole, I have to squeeze it into the size of a marble. Okay. I won't tell the satellite this, and I'll turn this into a black hole. Will the satellite be affected? Okay. Right. So the satellite doesn't care. As long as this mass is, so that's a general statement. You can, as long as you're outside the object, you can turn this into a point object and its gravity does not change. Okay? So the gravitational force exerted by a finite size, spherically symmetric mass distribution on a particle outside the distribution is the same as if the entire mass were concentrated at its geometric center. Okay? So that's what that means. Did you guys understand that? Okay. Here's the superposition principle. Let's say you have several objects and you want to calculate the force on this guy. The force on this guy is you calculate the force due to this guy, which is that. You calculate the force due to this guy, which is that. And the net force on that is just the vector sum of these two. Okay? So that's the superposition principle. You can calculate the force on an object using individual pairs and then just adding up the forces. Yeah. Now that works fine as long as you're not playing with black holes close by. Okay? If you have a few black holes close by, then that doesn't work. But then you'll have other things to worry about. So. What do you think this means? Variation of G. What is G?
Acceleration due to gravity.
Yeah, and what is it?
9.8%.
Okay, and that is what it is close to the surface of the Earth. Okay? So that's close to the surface of the Earth. So if you were this far away, then G would be different. Okay? So that's what this thing is saying. So the radius of the Earth is 6,400 kilometers. Let's say you were 6,400 kilometers above the surface of the Earth, then G would become, G would be that formula, 2 times R, so that 2 square would be 4. G would be 10 divided by 4, 2.5 meters per second square. Okay? So at that height, G is 2.5 meters per second square. Okay? All right, so that's what this is saying. G at this height above the Earth's surface, when h is 0 on the surface of the Earth, that is 9.8 meters per second square. Okay? And this gives you G at various heights above the surface of the Earth. And here's a table. So, for instance, at 6,000 kilometers, like I said, it's about 2.5 meters per second square. Okay? So, the further you go, the weaker gravity gets. And so that is what this is showing you. These arrows are showing you on the surface of the Earth, G is 9.8 meters per second square, and it's pointing towards the center. And if you go further away, the magnitude of the acceleration decreases. Okay? So this is called a vector field. At every location, you have a vector telling you the value of the field and the magnitude and direction of the field. Okay? So this is the gravitational field around the Earth. Okay? Again, what I want you to remember is that as you go higher up, the acceleration due to gravity decreases. Okay. So what do you measure in the lab? It's 9.8 meters per second square. What is G if you go to the tallest building in Daytona Beach? To the top of the tallest building in Daytona? It's still, yep, so it's still 9.8, okay? All right, here's Very interesting concept. Do you guys know how long it takes for the space shuttle to go around? I mean, the space shuttle is fairly close to the surface of the Earth. How long does it take to go around, not the space shuttle, the International Space Station?
5 minutes.
I'm sorry?
45 minutes.
90 minutes. Okay.
I'm sorry, did you say 90 or 9?
90. The International Space Station travels at about 8 kilometers a second. 8 kilometers is roughly from here to Ormond Beach in 1 second. That's the speed. Now, you guys have seen videos in the International Space Station. You're weightless in there. Okay. So what we're going to learn is the following. How fast does the Earth rotate? How fast? How long does it take for Earth to go around once? Per day. So it takes 1 day. Okay? Now here's what you're going to learn. If you could spin the Earth faster, if it rotated once in 90 minutes rather than once in 24 hours, at the equator you would be weightless. Here's the amazing part. So if you were at the equator, you could go for a walk and walk right into space. That would not be true for Santa Claus. He would still weigh the same. Okay? So at the equator. All right. Did you guys understand that? Yep.
So does that mean that close to a poles would we weigh more, or would it be the same?
Yep, so we weigh more at the pole. So here is the idea. So we'll get to that. All right. So if this is your speed and this is the radius of the circle, okay. So let's say you could be driving in circles on a flat road. Okay. Is your velocity changing? You're driving at constant speed. I'm sorry? Because you're changing directions, yeah. And so you have centripetal acceleration. And how large is the centripetal acceleration? It's v squared by r. Okay? And Mr. Newton says anytime you're accelerating, you need this much force to act on you. Okay? So when you're driving around in a circle, you're driving in a circle, what is providing the force toward the center? I'm sorry? Yeah, you have centripetal acceleration, but what force is giving you that acceleration?
The friction between your tires and the road.
The friction between the tires and your road. Okay, so the static friction force is providing that centripetal force. Okay, so what I want you to take from this is anytime you're going in a circle, you need this much force. How much force do you need? mv squared by r. Okay, and so we'll look at where the force is coming from. Okay. All right, so let's say, so here's the Earth, and let's say for now, the Earth is not spinning. So I'm going to draw two different perspectives. Okay, so here's the North Pole, here's the South Pole, here's the equator. Okay, now the Earth is not spinning, and so now this is a cross section. So you're standing at the equator. Okay, so what you're doing is you're standing on a scale at the equator. The Earth is not spinning. What is it doing? It's attracting you with this much force, mg. Okay. And why aren't you falling into the Earth? Because the scale is pushing you back with an equal and opposite force. And that is your apparent weight. That's what's measured. Okay? So why do you feel the hair on your head? Because gravity is pulling down and your head is having to push back on the hair, then that's why you're feeling it. Okay? If your head wasn't having to push back on your hair, you wouldn't feel it. Right? Okay. You guys understand this so far? Okay, so now let's do the following. Now let's spin the Earth. Again, we're still at the equator. So here you're at the equator. And we'll spin the Earth. We'll give you a velocity. Okay, you guys can do the numbers. We are traveling at about 1,000 miles per hour if you're at the equator. Okay, so if you're going around in a circle at constant speed, now you're accelerating. This is your acceleration. Centripetal acceleration is v squared by r. And you need this force, F equal to mv squared by r. Now, where is that force coming from?
Static friction force?
No.
Gravity.
It's gravity. Okay. Gravity never quits. Okay. Now, but you need a residual centripetal force. Okay. So in this picture, you weren't spinning, and gravity was balanced exactly by the normal force. Okay. Now that you're spinning, here's gravity, and so the normal force has to be smaller because you need a residual centripetal force. So the centripetal force is mg minus the normal force. And remember, this is what your scale measures. So soon as the Earth starts spinning, this is smaller. Okay? And you are weighing less on the scale. And if the Earth were spinning once in 90 minutes, okay, the normal force, this would be 0 because the centripetal force needed would equal mg, and you would be weightless. Okay. Okay. So that's what is being shown here. Okay. So the apparent weight is the force of gravity on you minus the normal force. Okay, and so the effective gravity is, again, if you rearrange all of this, is g minus r omega squared. And okay, so this is looking at it from the top. You're standing on the equator. Okay, you're going around in a circle, and okay, v is your omega is your angular speed. Okay? So if omega, the angular speed, becomes 1 revolution in 90 minutes, this number will equal g, and effective g will be 0. You'd be weightless at the equator. Okay? So as it turns out, you weigh the heaviest at the North Pole because you're not spinning. Okay? And at the equator, you weigh about 0.35% less. Okay? So if you weigh 100 pounds on the North Pole, if you walk to the equator, you would only weigh 99.665 pounds, all other things being equal. Okay. And if the Earth spun once in 90 minutes, at the equator you would weigh 0 pounds. Okay. All right. Now this is really cool, and it's slightly subtle. Okay, so if I build a building, what angle does it make to the ground? 90 degrees. Okay. It makes 90 degrees only at the equator and the poles. If you're in the northern hemisphere, so in this building, the North Pole is in this direction. The building is leaning towards the North Pole. So at any other latitudes, the building is not perpendicular to the ground. It's leaning towards the North Pole. So the Empire State Building leans 2 to 3 feet towards the pole. In the southern hemisphere, of course, you're leaning towards the South Pole. All right, so let's figure this out. Did you guys understand what we're talking? Okay, so for the tallest building, this represents a deviation of a few feet at the top. Okay. All right, so okay. So what we'll do is I'll exaggerate this slightly. Okay. So we've suspended, so let's say we've suspended a plumb bob from the ceiling. Okay. And what is this plumb bob doing at this place? It's going around in a circle around the earth as the earth spins. Okay. So what do you need? You need a centripetal force because it's going in a circle. You guys understand? Where is that centripetal force coming from? Well, it's coming from the force of gravity and the tension. And this tension, so there's the force of gravity and there's the tension, and these two add up to give you that. Well, you need a vector in this direction, so the tension is not, this is pointing towards the radius, which is perpendicular to the ground. So the tension is pointing slightly towards the pole. And you use a plumb bob to build your buildings. So in the northern hemisphere, the plumb bob is not perpendicular to the ground, it's leaning like that. And that's how you're building your buildings. Did you guys understand that? So all buildings, the only place where buildings are perpendicular to the ground are on the equator and at the poles. Anywhere else, they're leaning towards the pole. Okay, so every building really is a leaning tower of Pisa. Okay. All right. I'll pause for a second. Do you guys have any questions? Anybody need a break? Okay. All right, so I'll try and finish this chapter since I'm recording it. Okay. All right, do you guys remember? So this is a mass attached to a spring, and the force that the spring exerts, anybody remember the formula? Negative kx. Okay, where x is the distance you move it from the equilibrium position. Okay, and this guy is called the spring constant. Okay, now Newton was a very smart guy. He did many things. Okay, so here's one of the theorems he proved. Okay. So let's say this is a basketball, and you are inside the basketball. So Newton asked, what is the force of gravity on you inside the basketball? And what he showed was, inside the shell, as long as the shell is uniform, the force of gravity is zero, anywhere inside. Okay? So if a mass is outside of you, then the force of gravity on it is zero. Okay? What he showed was, so if you're here, this guy is attracting you in that direction, this guy is attracting you in this direction. Okay? Well, this guy is smaller, but he's closer, and so it compensates just the right amount. So the net force on you is zero. And so you can break up this thing into two shells everywhere. Okay? So what he showed was, anywhere, if you're anywhere inside a uniform shell, the force of gravity on you is zero. Okay? So what, if you were here, what is the force of gravity on you? What would be the force of gravity on you? It's zero. So if you were here, the force of gravity on you would be just due to this guy. This guy wouldn't matter. Do you guys understand? Okay. If you were here, the force of gravity would be just due to these guys. These guys wouldn't matter. Okay. So you can calculate this. Okay, so you can figure this out. So you can calculate what the force on you will be at various locations. And it turns out that this is the formula. R is the distance from the center. And look at this formula. This is exactly like that. where the spring constant is this guy.
So I assume that that premise of gravity being zero inside a shell doesn't apply to black holes because that's not like a perfect sphere shell. Or?
Well, so in black hole, if you went drinking beers with Einstein and asked him where is all the matter, Einstein will tell you that all the matter has already collapsed to the center, to a point. But we know that Einstein was wrong. But we can say that all we want, but we don't have a better answer. You know. All right, so here's a very interesting thing. Okay, so you know this is the force on the mass on a spring. So if you pull a spring, okay. So here's the equilibrium position. If I pull the mass to there, what will happen? It'll oscillate back and forth. Yeah. So if you dug a tunnel through the earth, remember if you stand here, the force on you is like a spring force. And if you jump into this tunnel, you'd oscillate back and forth, just like this mass attached to the spring. And here's the absolutely amazing thing. Anybody remember how long does it take for the space station to go around the Earth? 90 minutes. The period for this oscillation is exactly 90 minutes. All right, so if you dug this tunnel, you could go from New York City to Tokyo in 45 minutes. Okay. Now it turns out that you can dig the tunnel anywhere, and that oscillation time would be 90 minutes. Okay, but so it's 84.3 minutes. All right, do you guys remember the formula for gravitational potential energy? So what I'm going to do is I'm going to finish a few more slides, then we'll take a break, and then we'll do a little more lecture. And right. Do you guys remember the formula for gravitational potential energy? mgh, okay? mgh, U is that. Okay, that formula is good as long as G is constant. So built into there is that. So this formula is good for small heights above the surface of the Earth. Small heights being, let's say, 40, 50 kilometers and stuff like that. Okay, so as long as G is constant, then this formula is good to use. But it turns out this is not accurate. We just learned that G varies with height. Okay, so the more accurate formula is this. Okay, and I'm not going to go through the derivation. Here's the accurate formula for the potential energy. Okay, the gravitational potential energy is Gm divided by R, with a negative sign. So if you wanted to go to the moon and calculate the potential energy difference between when you're on the surface of the Earth and when you are far, far away, this is the formula you would use. Okay. So this is, again, so on interplanetary journeys, when you send stuff to Mars and stuff like that, this is the formula you would have to use. Okay, yep.
What's capital ME?
Mass of the Earth.
Oh, okay. And then.
So this is the gravitational potential energy between you and Earth.
Oh, okay, and R's distance.
So if you were here, R is this distance, center of mass distance to center. Yep.
Instead of capital MB for Earth, can you use it for any?
So yeah, so if you wanted to calculate the potential energy between, let's say, the Sun and Jupiter, it's minus G mass of one object times mass of the other object divided by R. Okay. You wanted to calculate the potential energy between galaxy 1 and galaxy 2, this would be the formula.
Oh, okay, so 2 ounces are just any two masses.
Any two objects. Yeah. Okay. Mm-hmm. That's what I'm looking for. Okay. So soon as I say something, you should be thinking on 10 different applications. Okay. All right. Yep.
Is there a reason that we use R for distance in this section instead of like D or S as we have before?
No.
Okay.
Have you done cylindrical? I mean, spherical polar coordinates in math yet? Okay. So x, y, z. So here the coordinates of this point in Cartesian coordinates are x, y, z. So the location of this number is given by three numbers in 3 dimensions. You can also give it in terms of r, theta, phi. These are spherical polar coordinates. That's where the r comes from.
Okay, thank you.
Yep. Just like we decided to call you Liam at birth, and we're going to call you Liam the rest of your life. All right. So now so again, this is the accurate formula for calculating the potential energy for 2 objects. Now, this is a pain in the neck to use because this, anyway, and you don't want to use this formula unless you have to. Okay. So, but again, like I said, if you're going on interplanetary journeys and stuff like that, if you jump more than 40 miles above the surface of the Earth, you got to start using this formula. So let's say you want to calculate the potential energy of solar system. You would calculate the potential energy of this pair plus this pair plus this pair, all the independent pairs. And that's that. Okay? You guys understand? Anybody know what this is? Escape velocity.
The speed you need to be going to escape Earth's gravity.
So, okay, so I throw this object up, it goes to a certain height and then falls back, throw it up faster, it goes higher and then still falls back. So the question is, can I throw it at a speed such that it never comes back? And like our friend said, so every object has a speed. Okay? From the Earth, it turns out that if you want it to escape, you need to shoot an object at 11 kilometers per second, roughly, for it to escape Earth's gravity. And that's escape velocity. Okay. So if you throw something at 11 kilometers a second, what will happen? It will go to infinity and will come to stop. What if you throw it at 15 kilometers a second?
It'll still escape.
It will go to infinity and have a speed of 4 kilometers a second. Okay? So what if you throw it at 8 kilometers a second? It'll go back down. That's why the International Space Station is not escaping. It's going at 8 kilometers a second, and so it just orbits. It's falling continually. Okay? So the International Space Station, as long as its velocity is less than the escape velocity, it's bound to Earth. Okay? So you can calculate the escape velocity from any object. Yep.
How fast is the moon moving?
Well, I think it's about 3 kilometers or so. No, not 3 kilometers. I don't know. Yeah. Google it. All right, so the escape, what this formula gives you is the escape velocity from this object from this distance, and all distances are measured from the center of that object. Yep.
So if the International Space Station is going 8 meters per
8 kilometers a second.
8 kilometers a second, how come it's not falling back to the surface?
I'm sorry?
So if it's not escaping Earth's gravity, how come it's not coming back to Earth's surface?
Okay, so here, I'm glad you asked. So let's say if I don't, so I'll drop this and it fell straight down. I gave it a horizontal velocity and it didn't fall straight down, it traveled a horizontal distance. Now, if I shoot it at 8 kilometers a second, the rate at which it falls down, the Earth curves at the same rate. So it's constantly falling, but it's never falling. Okay. All right.
It's
So,
like running on a ball.
I'm sorry?
So it's like it's running on a ball, kind of. Like the Earth is rotating.
I mean, you saw, well, so here's a, so if I shoot this, if there was no gravity, what would happen?
It would just go off until it ran out of energy, or just infinite?
It would travel an infinite distance and in a straight line. Gravity is what's making it curve. Its path to curve. And if that curvature, if your speed is such that that curvature matches exactly the curvature of the Earth, that distance will never decrease. Okay. So here's a very interesting thing. Let's look at this formula. Okay. So again, this is escape velocity from this mass, from this radius. Okay. So from this object, from the surface, from the Earth, it's 11 kilometers a second. Where r was this distance. What if you're trying to escape from this point? Will the escape velocity be the same? No. R has increased, and so the escape velocity will be smaller. Okay? What if you're trying to escape from infinity? Escape velocity is 0. Okay? Right? This thing has gone to infinity and escape velocity is 0. You've already escaped. Okay. Now let's go the other way. Okay. What is the fastest anything can travel? I'm sorry?
Speed of light.
Speed of light is the speed limit. Okay? So let's do the following. We'll take an object and start squeezing it. Make r smaller. Take this object and start squeezing it. The escape velocity starts increasing. Okay? If you squeeze it to a point where this escape velocity becomes the speed of light c, you've converted it into a black hole. That's what a black hole is. Yeah. Go ahead.
Yeah, well, you may not have the answer, but why exactly is the speed of light top speed? I mean, I've heard that everywhere, that, oh, it's
Mhm.
the fastest you can go, but I've never, nobody's really, I've never heard the explanation as to why.
That's how the laws of nature are. Yeah, I don't know. That's the speed at which all massless particles travel in vacuum. That's a photon. So I haven't answered your question. That's how just nature is. So the laws of physics are explaining nature, and that's how nature is. So before Einstein, the speed limit was infinity. All right, so we've learned the following. You can take any object. So for instance, if you take Earth, the escape velocity from Earth is 11 kilometers a second. You can take Earth and squeeze it to the size of a marble. And at this point, the escape velocity is c. You can take the sun and squeeze it into, by the way, from the surface of the sun, this escape velocity is about 600 kilometers a second. You squeeze it into the size of 3 kilometers. 3 kilometers is from here to the beach, or here to US 1. And you can turn the sun into a black hole. Yep. Now, of course, if you squeeze all this stuff within this radius is called the Schwarzschild radius. as far as Einstein is concerned, everything will fall into to the center, to a point at the center. All right, so there's the escape velocity. Okay, so here are escape velocities from various objects. From the sun, it's about 600 kilometers a second. From the earth, it's 11 kilometers a second. So if you want to orbit the earth and you want to be bound to the earth, you have to travel slower than 11 kilometers a second. Okay, so now in one swell swoop, you know the speeds, the upper limit of the speeds of all the satellites going around the earth. There are about 11,000 objects orbiting the earth. Okay? And their speeds are all, okay, so you guys can read this stuff. All right. So what we are saying is the following. So here's an object. So let's say this is the Earth and this is a planet going around. So a planet is bound to this star. Okay? And that will go around forever. There are comets that will go around like that, okay, that are sometimes in unbound orbits. Okay? So if you take the total energy of an object that is bound, it's less than zero. If it's unbound, its energy is greater than zero. And if, okay. So if the total energy of an object is less than zero, it's either going in a circular or elliptical orbit. If its energy is zero, exactly zero, it goes in a parabolic orbit. And if it's if it's in a hyperbolic orbit, then its total energy is greater than zero. Okay, so, and those are the conic sections. Okay. And Kepler summarized this. He didn't know why this was happening. He observed the motion of planets. Well, actually, it was Tycho Brahe who recorded the motion of planets, and Kepler summarized them in his 3 laws. Okay. So what he realized was all planets move in elliptical orbits. They're bound orbits. Okay. That's the first law. The second law says the radius vector. The second law says the following. So here's a planet going around. What he says, the second law says the planet sweeps out equal areas in equal time intervals. So if the planet went from here to here in a month, that's the area swept out. Went from here to here in a month, this area is equal to that area. This area is equal to that area if the planet goes there in equal time intervals. Okay, so that's Kepler's second law, and this is Kepler's third law. The period of a planet divided by its orbital radius is constant. It depends on the central mass. So what Mr. Kepler says is, if you have all these planets going around the star, you can take the period for every planet, divide by radius cube, you get the same number. So this is Kepler's third law. Now here's a very neat thing. Okay, how long does it take for Earth to go around the sun? 365 days. You guys know this? Do you guys know how far the Earth is from the sun?
93 million miles.
I'm sorry?
93 million.
Very good. You guys know these two numbers? You can go home and calculate the mass of the sun. You don't have to trust any table. Okay, do that. How long does it take for the space station to go around the Earth? I'm sorry? 90 minutes. You know how far what is the radius of its orbit? I just told you that. 6,400 kilometers or 6,800 kilometers. You know that? You could calculate the mass of the Earth. Did you guys understand that? Okay.
So the radius.
Just a second.
Okay.
Just a second. So, what is this? A spiral galaxy. At the heart of all galaxies, we believe that. Come back here. So, at the heart of all galaxies, we believe that there are massive black holes that can have 1 billion solar masses. How do we know that? Exactly like this. What we have done is we've looked at stars orbiting around there. We see nothing there, but from its period and radius, orbital radius, we can calculate the mass of that central object. Did you guys understand that? So that's how we know of massive black holes at the center of galaxies. So you have to observe stars that are going around in circles. You measure its periods, and you measure the radius of those stars. I mean, orbital radius, and you can get the mass of the attracting object. Yep.
I was just a little bit confused on the definition of the Fred law.
Okay.
So the different orbits, you said they're all.
So what Mr. Kepler is saying is Kepler was studying our solar system. And before Kepler, we didn't know this. So this is our sun, and our sun has several planets. And what he found was the amazing fact. For every planet, you measure its period, you measure its orbital radii, take the cube of that, and you get the same number for all different planets. Okay? And that number, Kepler didn't know this, that number turned out to be related to the mass of the sun. You had to wait for Newton to come and tell you that. Yep. All right, let me get done with this, and then we'll, so here's the mass of the sun. You can calculate the mass of the sun using parameters for the Earth. Okay, so satellite speeds can be calculated using this. The orbital speed decreases as 1 over r to the power half. Okay, so if you're 4 times further away, your speed is twice as small. That's what that formula is saying. Okay. So if this is v, and if you're twice as far, your speed is 4 times as far, your speed is v by 2. Okay. All right, let's stop now. We'll take a break, and then